All right, so this video is going to be on electrophilic aromatic substitution, EAS, of substituted benzene. So we really want to talk about electron donating groups and electron withdrawing groups and their effect on the benzene's reactivity, and basically where the new electrophile is going to end up, right? So remember, electron withdrawing groups I like to draw in blue. Like this ammonium here had a straight up positive charge, right? This aldehyde has a delta positive charge. And so those are pretty much the criteria for identifying an electron withdrawing group as a substituent on benzene. NO2 was a tricky one because it was like low-key positive, right? You had to really draw out that resonance or that Lewis dot structure to see that, because it's overall neutral. Okay, it doesn't have a charge, so you don't have to indicate that usually. Now our red electron donating groups, let's draw one that's more analogous to the ammonium group, but that amine has a lone pair, can donate into that ring. We also have, let's say, a chicken foot. Got to have our chicken foot in every lecture, right? That benzene ring with the alkyl group, of course, is an electron donating group. And then we have, let's say, like a methoxy group, OCH3, okay? Now we know that the lone pair on the oxygen can also donate into that ring. Now, what does that really do? Okay, so when we have electron donating groups on a benzene ring and we're doing an electrophilic aromatic substitution reaction, it increases the rate of that reaction, because I think of it as like you're donating electron density into a nucleophile, right? It's going to be crazy reactive. Now, on the other hand, electron withdrawing groups decrease the rate of that reaction because you're withdrawing electron density, and now that benzene ring is no longer a strong nucleophile, or it's not like a very good nucleophile, or it's worse of a nucleophile. Okay, so let's see what I really mean by that. Like, what are you talking about? Rate of reaction, right? So let's draw out a generic benzene ring, not generic, it's just a benzene ring with bromination reaction, right? So we have, of course, our elemental bromine and our iron bromide for our Lewis acid to give our bromine substituted benzene. We have the methoxy. Remember, that was an electron donating group. That's why I'm drawing it in red. That can give us, I'll draw a couple different products here because, as you'll see, that's what we would get. And we're going to get a mixture of the bromine at the ortho position as well as the para position. And I don't know, it doesn't matter, 40-60, let's say. So basically, this reaction right here is much faster than benzene, the one in black, right? Benzene is just like the standard. And so when we're comparing the rate of reaction, we're always comparing it to benzene, okay? So electron donating groups are faster than benzene. The nitro group, as we established, is an electron withdrawing group. So when we do the EAS with bromination, we can have a bromine at the meta position, right? In this case. So again, we'll explain later. But we might also have like a little bit of some other things. So there's, again, like I said, there's 5 different spots on this particular on this benzene ring, and so we're going to get a mixture for sure. But it's all about like what is the major product, right? Blue is much slower than benzene, and that's really what we're talking about when we're saying like rates of reaction. Benzene is the 0 point, and it's the standard in terms of comparison. So the question again, as I mentioned, I was like talking to ortho, meta, para, like where do the substituents go? Like how do we know where they go? Well, it's actually pretty not straightforward. What am I kidding? So it's just fun to explain, I think, and fun to like kind of answer that problem, right? Because it's really detailed. We tie in a lot of different things. But the question is basically, does it go to the ortho, the para, or the meta position? When we're talking mono-substituted, the 2 ortho positions are equivalent. So it doesn't matter which side they go on, they're the same. And then, so we'll have the ortho para directors. And then the meta positions are also the same, and so we'll just have meta directors as well. So What do we mean by that is force a substituent to go in the meta position or force it to go in the ortho or the para position. So there's 3 types of substituents, okay? Now, I know basically we'll have a substituent that is an ortho-para director, but is also an activator. So when we talk about activating benzene, we mean that it is making the reaction much faster. So it's like you're activating that benzene and it's reacting much faster because it has an electron donating group on it, okay? I'm choosing poopy brown here because this one's not cool because it's like counterintuitive. We have an ortho-para director that is also a deactivator, and you'll see why that's kind of counterintuitive perhaps, because the meta directors are electron withdrawing groups, right? And they more or less deactivate, right? They are deactivating, but we don't necessarily classify it as deactivated. It's kind of assumed, right? The poopy brown one is the weird one that we're classifying even further. So I didn't want to draw this out, and I just wanted to copy and paste that for you guys so that you didn't have to watch me draw all this. But this is a graph of breakdown of all of the substituents on benzene, and the top that I just highlighted in red, those are increasing in activation as you go from the bottom, R, to the top, the amines. Okay, and as you can see on the right side, they're activating groups. They're also ortho-para directors. Now, the poopy brown is the halogens. Okay, we already classified the poopy brown above. Now, the blue, as you can see, that arrow is increasing in deactivation. Okay, and that means that CHO, of course, is an aldehyde as you go all the way down to an ammonium group on the bottom. Okay, now the dotted line represents the kind of the separating point between ortho-para directors and meta directors, because although halogens are electron withdrawing inductively, they can actually donate with their lone pairs. That's why I drew them in pink, to kind of create a resonance structure that's kind of supportive of an ortho-para director. And so they're in a class of their own, okay? That's why they're poopy brown, because they're kind of the mixture of the top and the bottom. They're electron withdrawing group, which typically means that they're going to be meta directors, but they're not because they have a lone pair. Okay. Now, of course, we got to get that practice in, okay? Because these ones are just, there's a lot of stuff going on, right? So we're going to get plenty of practice here. We're going to draw out some structures, and we want to know if they're activated, deactivated, or as well as what kind of director it is. So the director type, is it ortho-para director or is it a meta director? Okay. So of course, per usual, I want to draw out all of these schemes here, and I want you to pause the video when I'm done drawing them out and then try them on your own and see if you get the same thing as me. Okay, so remember, the electron donating groups are basically atoms that'll have a lone pair. They're going to donate into the ring. Those are ortho-para directors, activators. The electron withdrawing groups are the delta positive atoms directly bound to the benzene or straight up positive atoms bound to it. And those will withdraw electron density, deactivating that benzene ring, making it less reactive, and then also typically being a meta director. They will also, or we also have the halogens, which are in a class of their own, which they're deactivating because they withdraw electron density, but because they have those lone pairs, they can they are ortho-para directors. Okay, so pause the video, do this on your own, see if you can get the same thing as me. There's a lone pair on that amide group, right? So it's activating. Now, what is its director to, like? Is it ortho-para director or is it meta director? This is, of course, an ortho-para director because it is an activator, right? Those are hand in hand. They always go together. Now, where does it go? Well, again, it's the ortho position on one, and we have to draw another product where we have the nitro group on the para position. the substituent itself remains the same. So all you have to do is redraw the compound and then put the new substituent at the ortho and the para position. Sorry, I was just zoomed out the whole time. I didn't even realize it. I was just in the zone. Oh, cam zone. Or out of zone. I don't know how it goes, you know. Anyway, carbonyl groups. We know that carbon directly bound to that benzene is a delta positive. It's a deactivator, which means it's a meta director. And so we just draw out that substituent or that starting compound and then just draw a bromine on the meta position. Remember that circled other meta position is the same. We don't have to draw another one there. Or we could have drawn it either spot and it would be equivalent. Deactivator for that carbonyl group again. Let's do meta nitro group this time. This CN triple bond, of course, it's a deactivator. We established that before because of that delta positive on the carbon as well as a resonance structure that supports it. We're going to draw the nitro at the meta position. Now I'm just doing the nitration reactions just because that's what I did. You could insert any kind of reaction here, right? So any EAS reaction, and then you would put the substituent at the same exact spot. So this one would be an ortho para. Now, if I did chlorination or bromination or alkylation or acetylation, like they're always going to be in the ortho para position or the meta position, no matter what. Okay. There are going to be limitations to those reactions, though, and so I will get into those in a little bit, or in another video, actually. Deactivator, of course, but it's an ortho para director. Boom. So we get to draw two different products. NO2. All right, the last one is the alkyl group. As we know, it is an activator. It inductively donates those electrons to the benzene ring, and we get the ortho para direction as well. So ortho product and the para product drawn here. And again, that carbon sigma bond between the benzene ring and the ethyl group, that is in fact a sigma bond, and so it's free to rotate. That's why the ortho positions are equivalent. All right, this one's fancy right here. I like this one. It's because we have two benzene rings in it, right? So where do you think this bromine is going to go when we do EAS, right? With our iron Lewis acid, of course. We have an alkyl group essentially attached to that benzene ring on one side. And then we have a carbonyl group attached to the other benzene, right? So the blue is clearly deactivated and the red is activated. So if we're going to add a bromine anywhere, then we should, of course, add it to the activated benzene, right? And so what we do is we view that as just an alkyl group and we treat it as such. So we draw the bromine on that benzene ring, and then we draw it in the ortho and the para position because alkyl groups are ortho para directors. And that's all you got to do. Super fun, right? It's a nice little OChem Sudoku puzzle. We got plenty of those to do, so keep getting your practice for sure. You might have a question. Why the substituent activates or deactivates a benzene ring? Why does this happen? Because we keep talking about like, okay, yeah, it just donates electron density or withdraws electron density. We know that's not a sufficient answer, right? We got to talk about energy curves, of course, the diagrams. And so let's talk about the intermediate. Okay, so once we add an electrophile to a benzene ring, we form this carbocation intermediate. Now, this is the focus of this discussion of why a benzene ring is activated or deactivated. Okay, so if we have, sorry, I'm gonna move this over here right quick. There you go. All right, I have three of them. So of course we're gonna compare the electron donating group. Remember, this is donating into the carbocation intermediate the whole time, right? So the electron density is going into this carbocation intermediate, so it's helping to stabilize the positive charge, right? If you're putting electron density into a positive area, you're stabilizing it, making it less positive. In contrast, the electron withdrawing group, of course, withdraws electron density even more so, and so it's creating a benzene ring that's even more positive. So that's going to be destabilizing that, right? It's going to be pissed. Now, of course, the middle one is just benzene. So we're comparing the EDG to the benzene to the EWG. So now let's draw an energy diagram associated with these three processes. Okay, so remember Hammond postulate states that in an endothermic process that the product and the transition state, they look similar, as opposed to an exothermic where the reactants and the transition state look similar. So what that means is in this endothermic process, in this step 1 of EAS, we form a carbocation, so that's going to be higher in energy. And if we can stabilize that carbocation, like with an electron donating group, we can lower the energy of that intermediate, which in turn lowers the energy of the transition state. So that's why that bottom curve represents the intermediate for the electron donating group on that ring. And then the middle one is just the intermediate for a regular benzene. And then the top blue one is the intermediate for an electron withdrawing group. Okay, so again, those electron withdrawing groups withdraw electron density. That's why the energy of that particular intermediate is higher, as opposed to the electron donating group, which donates and stabilizes that carbocation intermediate, lowering the energy of that intermediate, which also lowers the energy of the transition state. So since we lower the energy of the transition state, we're lowering the activation energy, which results in a faster reaction rate, and this benzene ring is deemed most activated. Now, thinking about it in its most simple terms, like this is not even like necessarily super science based, but like to draw a resonance structure with an electron donating group, and that puts a negative charge right there on that benzene ring, and that negative charge is angry. Grrr. So it's super reactive, right? It's activated. Just like this little girl from Look Who's Talking. So that's kind of like how I think about it. But of course, we can, obviously, when we need to discuss it, we need to discuss it in depth with the intermediate in consideration, and the energy levels and the diagrams, etc. So let's talk about the orientation effects, though, in the substituted benzenes. So we have ortho para directors and we have meta directors, right? So why does this happen? What's going on here, right? So let's say we have this amine. Remember this nitrogen, this NH2 on the benzene ring is actually called an aniline. It's got a common name, aniline. And we can draw another resonance structure for this guy, right? Boom. Looking right there. So you can see that there's a negative charge on the ortho position as well as the positive, or as well as the para position. So that's kind of like how I like to think about ortho para directors. They donate electron density into the ring, and they put a negative charge on that ortho and the para position, right? So that's obviously the most nucleophilic site, so it's going to go there. But really what we need to look at is, that's kind of to help you remember it, but to discuss it in detail again, we have to look at the intermediates of the different substituted products. So if we were putting it at the ortho position, we can put a positive charge right at that carbon where the nitrogen is. If we put it at the the meta position, we would have a positive charge at the para position. And then we can put the electrophile at the para position, and that puts the positive charge on the meta position. Okay, sorry, that might be wordy, but basically we have ortho, meta, and para substituted intermediates here. Now, of course, we have resonance structures. Okay, so we have to look at these resonance structures to help us justify our positioning of that substituted or of that electrophile on the new substituted benzene. So we've got our resonance structure where the nitrogen actually stabilizes that carbocation intermediate, making it a positive nitrogen. We can neutralize that nitrogen, shifting our pi electrons again, and we've got another resonance structure here. We got a new positive charge. We can, of course, shift another pi bond to put the positive charge at a different position. So what we've got here is 1, 2, 3, 4 resonance structures. The positive charge is like kind of flowing around that entire benzene ring, including on the nitrogen. Okay, so let's look at the meta group, meta substituted intermediate. So we've got that positive charge shifting from the para position to the ortho position, right? Boom. We'll go ahead and shift that again with the moving the pi bond or the pi electrons around. And there we go. We got the positive position or positive charge on the other side. Can you see another resonance structure? I can't. At least not one that moves a positive charge around, right? So the para position, we can do the same thing as the ortho, where we move, or I guess the ortho and the meta, but the para position and the ortho position are very similar in that we can put the positive charge on the carbon where the nitrogen is, and then another resonance structure would stabilize that positive charge with the nitrogen's lone pair. And then we move things around again, and really what we end up with is 4 resonance structures for the ortho para substituted product, or intermediate rather, and then only 3 resonance structures for the meta substituted intermediate. Now we know more resonance structures, then the more stable this compound or this intermediate is, right? So that is the justification for the ortho para directors. They have more resonance structures, and that's all because of the location of that positive charge and the ability of that electron donating group to help stabilize that positive charge. Okay, so more resonance structures, more stable intermediate, which means, remember that intermediate is the product of the endo group, right? So if we're lowering the stability, or if we're increasing the stability of that and lowering the energy of it, then we're lowering the activation energy, which means we're going to get a faster reaction if we do ortho or para substitutions. Okay. Now looking at the nitro group, remember the nitro group was low-key positive on the nitrogen, and so we have to have what we want to do is look at what this electron withdrawing group will do in terms of directing the new electrophile. Okay, so just as above, we will draw the first position. I get the ortho, meta, and para substituted intermediates, and then all of the resonance structures. All of the resonance structures therein. So go ahead and, if you want, try and draw all of them out and justify on your own using the same logic as above. What we should do is, of course, draw the positive charge on that nitrogen. So that way, in this first resonance structure in the ortho substituted intermediate, we can see we have 2 positive charges right next to each other. That's highly unstable. Or let's just leave it as unstable, right? Because it still can do some stuff when it's in that position. But what we want to do is continue on by drawing some more resonance structures, shifting that pi bond around, moving the positive charge. And let's go ahead and draw it again. Boom, 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 boom. Positive charge there. So there's 3 resonance structures for that guy. Now what we do is same thing as before, shifting that pi bond around to kind of move that positive charge to a different location. Hopefully you guys got this process down by now with the resonance structures and where the positive charge ends up. And it's really important that you just remember that where the electrophile went is sp3 hybridized carbon, and it cannot be involved in these resonance structures. Okay. So the last one on the para substituted intermediate, we have that positive charge on that nitrogen, as well as the carbon right where it's bound to, and so that's going to be unstable again, right? We don't like 2 positive charges right next to each other, and that's really what we're using to justify the location of the electrophile with an electron withdrawing group on a benzene. Meta is going to be preferred because the three resonance structures that we can draw for that intermediate do not put the positive charges next to each other, and so it's going to be more stable, and so therefore more likely to form that product. So that's going to be the desired product when we have an electron withdrawing group. All right, so what about if we had an alkyl group? How does this work? Because we don't really have an electron, we don't have a pair of, like a lone pair, right? So we can't just kind of create a pi bond and move things around. It is an ortho para director nevertheless, and that's because if we have a positive charge, iPad, let me zoom in on it or make it bigger. There you go. Positive charge on that carbon with the alkyl group attached to it. Let's go ahead and draw what was really there, which is a vacant p orbital. Okay, it's the positive charge. And remember, an alkyl group, at least like the methyl group, will have hydrogens kind of floating up and down. This bond right here, this sigma bond that's there, can overlap with that vacant p orbital. And remember from previous chapters, this process is called hyperconjugation. Okay, and so hyperconjugation helps stabilize that vacant p orbital, or that positive charge at that position. And so it's very similar to the electron donating groups that have lone pairs, but it's just via a different process. And then of course there's also the idea of inductive effects as well. That alkyl group is donating electron density through the sigma bond as well. And so that's how we explain alkyl groups being ortho para directors. Okay. All right, so my kids are fascinated with bees right now. So as always, I guess. So I went to this pet shop to get some bees. I was like, hey, can I get 12 bees? And they gave me 13. I was like, what's up with this? He said, the last one's a freebie. Woo!